Hey folks, welcome back. This is our second lecture on 11.1. We're going to talk some more about the logistic population model that I introduced at the end of last time. And remember last time we started by talking about the rate of change of population. We transitioned to these differential equations instead of difference equations. And we're talking about the rate of change of population. And our assumption then was this was just K times P. And we kind of investigated that model, and I used it to look at some data on US population. And we saw it didn't really fit. Maybe it fit for a while, maybe it fit with different growth rates in different periods. And this, you can think, if you thought about this model, in fact, as the number of people with the coronavirus right now, that's increasing exponentially as well. So this model that we derived with exponential growth, this differential equation, completely describes the number of coronavirus cases right now in the US and Italy, and hopefully soon will fall off that exponential curve and the number of cases will decrease. Right? If I'm plotting here number of cases against time, I'm literally thinking in that case P of t is the number of cases, and there's time. We don't want this to continually exponentially increase, right? Because I think we all know why. But this is not a reasonable model for many things because population doesn't tend to grow without bound, right? There are limits. The demographers talk about carrying capacity. There's a maximum number of people that a given country, region of land can carry. Is there enough water? Is there enough food? Is there enough space? All of those things lead to kind of a downward pressure on population growth. So as the population gets bigger, the rate at which it's increasing changes. And the rate at which it's increasing was that K, and we assumed it was a constant in our first model, and so we introduced this new improved model where if we look at the growth rate itself, right, you can think of this literally as plotting the fractional growth rate, so 1 over P dp dt, and in our original model that was K, and so it was a constant, there we go. But in our new model, the rate of growth is this thing essentially, the multiplying the P, and what's happening is it's a decreasing function. You can see it has slope minus K is the slope. The y-intercept for this green thing, if I just plotted that green thing as a function of population here, the y-intercept would be what? K times M. So the y-intercept is K times M, and I'm assuming K is positive here, I should say, and then M is positive as well. And so we get this decreasing growth rate. And that's kind of where we were from last time. So now we want to analyze this. And remember last time we began the analysis by looking at regions of increase and decrease. And so let's make the same approach to this logistic equation. And let's define the idea of equilibrium values. Equilibrium values are places where the rate of change of the population is zero. Right? It's literally a maximum in the population or a minimum in the population. It's a moment when the population stops changing. That's just from Calc 1. So in this case, the equilibrium values are when the rate of change of population is equal to 0, and so we get this equation, right? And it's already factored. K is a constant, and I said M was greater than 0. I think I also want to say K is greater than 0 here. We're thinking about population increase. The only way the population can be, the only way the rate of change of population can be 0 is, well, if M is equal to P, that's what I'm trying to say. In other words, the population is equal to M, looking at this term and saying when is this factor 0, this is just a polynomial in P, so either M minus P is equal to 0, so P is equal to M, or P itself is equal to 0, and there are our two cases. So there are the equilibrium values in this case. Either population is 0 or it's M. And P equals 0 is not very surprising, right? There are no people. So the rate of change of population should probably be 0 if there are no people. If the rate of change of population is this constant M, and I'm just telling you it's positive, but we don't really know what that represents yet, we'll work that out from the modeling, then we come up with a rate of change that is constant as well. So in other words, if the population ever hits the value M, it will stay there forever because the rate of change is 0. Notice I'm calling these equilibrium values, and these might look a little like what we talked about in Calc 1. In Calc 1 we talked about critical values, but remember the critical values are where, for example, the critical values are where are values of time when the rate of change of population is 0. So in Calc 1 we define critical values, but they were values of the independent variable where the rate of change was 0. Well, the independent variable doesn't appear here, right? These are, remember, what we called autonomous equations. So the independent variable, in this case time, what in Calc 1 we would have called x, doesn't appear in the equation. So this is an equation that is kind of the form dy dx equals some function. Well, in Calc 1 we dealt mostly with functions of x. But that's not what we have here. We have a function of y itself. That's what we mean by an autonomous equation. So critical points are values of x. Equilibrium values are values of y that make the derivative 0. That's the distinction, if you're wondering. Okay, so let's actually build a little phase diagram here. I'm going to look at the p-axis. I know what happens to the first derivative of p. That's what we just calculated. The first derivative of p is 0 when p is equal to 0 or p is equal to m. So when I put p equal to 0, the first derivative is 0. When p is equal to m, the first derivative is 0. If p is negative, I don't care because this is a model that talks about population, so we're not interested in those values. So what happens when we're between 0 and m? So let's say at m over 2. At m over 2, we go up here and we plug it in. We get m minus a half of m. That's a half of m. We get a half of m here. And so this whole thing is positive. Right? I'm literally plugging in p equals m over 2, and I'm asking what's the value of that derivative, and the answer is it's positive. And then I'm going to say what happens when m is bigger than that. Sorry, when p is bigger than that. Let's suppose it's 2m. Suppose it's all the way up here at 2m, not to scale. Well, then this factor will be negative. This factor is positive, and so overall the rate of change of p is negative, which means p is decreasing in that region. In other words, p is decreasing when p is bigger than m, and it's increasing when it's between 0 and m. I'm going to bring this together on the next page, but first let's have a look at concavity. All right, so if we want to think about concavity, we want to think about the second derivative with respect to time. So if we go through and differentiate this, we're going to differentiate implicitly, and remember that p itself is a function of t. You might see this written. All that says literally is p is a function of t. So k is a constant, so I'm going to ignore it. So I've got two factors here. I've got the m minus p. I'm going to differentiate that with respect to, what am I trying to say? I'm going to differentiate that with respect to p and use the product rule. Sorry, with respect to t. So we're going to get minus dp dt multiplied by p, and then the other term is when we hold the m minus p constant and we multiply by the derivative of p with respect to t, which is dp dt. And so we have a common factor. I'm going to pull the k out. We have a common factor of dp dt. I'm going to pull that out. So there's a dp dt in both terms. There it is. Sorry, there it is. There it is. There's a k in both terms, and what I'm left with is minus p plus m minus p. Is that right? Yeah. So m minus 2p. So this is k. What's in the bracket there? M minus 2p. And we also know what dp dt is, right? Because dp dt is the rate of change of the population. Here it is. It's in this nice equation right there. So I can just plug that in. So this becomes k squared m minus 2p, and I plugged in dp dt. That's where the extra k came from. I also end up with a term m minus p and a term p. Right? I'm literally plugging in for this. This thing is k m minus p times p. And I plug that in. There's the k m minus p, and one of the k's is there. Or the m minus p and the p. One of the k's is there. All right, so where does the concavity potentially change signs? The potential inflection points are where the second derivative is equal to 0. So the potential inflection points are where we have 0 is equal to k squared m minus 2p. I'll get that out of my way. M minus p, p. And there are three of them. From here, the population is m over 2. From here, the population is m. From there, the population is equal to 0. Right? These are the places where the second derivative is equal to 0, and so they're potential inflection points. Potential because what I'm saying is that the derivative doesn't have to change sign there, but it certainly could. And I can draw an axis, right? Here's my p-axis. In Calc 1, we would draw an x-axis, or in this case, a t-axis. We've got three potential inflection points at 0, at m over 2, and at m. And let's look at the concavity. Let's look at what the second derivative of p with respect to t is doing. So I know that it's 0 here, I know that it's 0 there, I know it's 0 there. Now let's just plug in some numbers. If I put in a number that's much bigger than m, so much bigger than m, then m minus twice a number that's much bigger than m is going to be negative, m minus p is going to be negative, and this is going to be positive. So this whole thing here is going to end up to be a positive. I'm just plugging in test points. So let's plug in a number like m over, well, let's plug a number in here. A number to test over here would be like m over 4. So if I plug m over 4 in here, I have m minus a half m, well that's positive. This is m minus a quarter of m, that's positive. This is positive, so all of that is positive. And in this region, between m over 2 and m, so you could choose, for example, 3 quarters of m. And if I plug it in here, I've got m, that would be minus 3 halves of m, so that's going to be negative. M minus 3 quarters, that's going to be positive, and that's going to be positive. So this whole thing is negative. So there's our concavity. We actually don't care about what's happening down here because this is population, and we're not interested in population below 0. So let's put this information together in a little chart and use it to draw a picture. All right, so here I've summarized what we just talked about. We looked at the first derivative, we looked at the second derivative of p with respect to t. We found these key equilibrium points, and I've labeled them on the, well, not that one. I found the equilibrium points, and I've labeled them on the graph here, the equilibrium values. We know that if the population is 0, it stays 0 for all time, right? The rate of change of the derivative is 0. So there's one of our level values of the population. P equals 0 is an equilibrium, and P equals, that's a terrible line, but P equals m is an equilibrium value. Let's pretend that was m. So this is P equals m. Those are our two equilibrium. They don't change, so they're flat curves. The population is equal to m for all time. The population is equal to t for all time. We saw something interesting happening in between. We saw that when m was 2, the concavity changes. Sorry, when p was m over 2, the concavity changes. So there's a graph of that value, and that's where the concavity changes. Now, what did we see? Let's draw a few curves. Let's use all this information to draw a few curves. Let's say we have an initial value down here. There's our initial population. It's less than m over 2, but it's positive. If it's less than m over 2, then it falls in that region because it's less than m. And so the function is increasing. It's less than m over 2, and so it's concave up. But it's only concave up until you get to m over 2, because at m over 2, things become concave down. So this is an increasing concave up function. Increase, 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 concave up. Looks like that. But at m over 2, the graph must change to concave down, because if the population's between m over 2 and m, it's concave down. But as long as it's still below m, it's got to be increasing. So it's going to increase, but it can't cross this line, because if the population is ever m, it stays m for all time, and so it must continue increasing, but be concave down and asymptote off towards that line, p equals m, as m gets large. Right? So this is an inflection point. This is where the concavity changes. If I start with a population that's bigger than m over 2, but still less than m, so if I start with a population here, if that's our starting point, then it's going to be concave down for all time, but increasing. Oh, that was a terrible line. But you get the idea. It's really hard to draw this nicely. But if it starts down here, it's going to be concave up for a while. That's probably too sharp. It's going to be concave up for a while, and then it's going to be concave down, and they're all going to asymptote up towards the value of m. Now, if I start with a population that's above m, then it's decreasing and concave up. So if it's decreasing but concave up, it looks like this. Decreasing, concave up, again, can't cross that line. So here's a starting value that's bigger than m. There's m. We're bigger than m. So it's decreasing but concave up. So you get an idea of what this looks like. We can decide what m must be from this. M is the maximum population, right? The maximum population is that capital M. I just introduced it in the model before, but this model has a maximum population m. We'll call it the carrying capacity. Right? Because anything bigger than m, if the population's ever bigger than m, it will decay down to m. If it's smaller than m, it'll increase up towards m. So m's called the carrying capacity. It's the maximum number of people that this environment can sustain, and of course it depends on the growth rate and all of the other things, exactly which of these curves you're on, where you start, the p0. But there's an intrinsic property in this model which we can think of as the carrying capacity, which is the maximum stable population that this model is going to allow. Right, here's another example. The population starts really, really small. It takes a long time to grow. The growth in that region is essentially going to be exponential for a while, and then it's going to hit the inflection point at m/2. It's become concave down. It's going to continue increasing for all time, but it's going to increase towards that carrying capacity, m. Let's have a look at how we might actually solve this equation, just quickly for fun. All right, so this is another example of a separable dE. Remember how we treated the last one? We had a differential equation that looked like that, and I rewrote it so all the p's and the dp's were together and anything else was on the other side, and then we integrated it and we could solve it that way. Well, this thing can be solved in a very similar fashion, because I can write this as, this time we're going to end up with a quadratic in the denominator there, but I'm going to divide all of this onto the left hand side, and then on the right hand side I'm just going to leave kt. Just an editorial comment, that should of course be k dt. I haven't fixed the video, but it should be k dt, which I then integrate to get kt. Sorry about the error. Now, this is what you will recognize from Calc 2 as a partial fraction problem. This has a factorized quadratic in the denominator, so we'll use partial fractions and we'll just separate it. And so just doing that, you'll see you end up with something like this. If you put it back over a common denominator here, you'll get an m minus p, you get a plus p, you're left with an m. So I haven't written it yet, but you need to factor 1 over m out the front. If you do the whole partial fraction decomposition, you'll come up with that setup. Now, we're going to look at the interesting part of this. We're going to assume, just for simplicity, that the population is positive, but it's less than m, because that's the region where interesting things are happening. Remember, when the population is positive but less than m, we're talking about this region here. And so that's the interesting region. Up here we've just got exponential decay down to that carrying capacity. We're interested in what's happening in the region between 0 and m. And so I'm going to integrate this, and the integration again is very straightforward. You've done Calc 2, then this is log p minus, because we've got the minus p in there, so that'll come out the front, and m minus p. And this is an absolute value, and so I integrated the other side already, kt plus c. And I can actually drop the absolute values here because p is positive and p is smaller than m, so m minus p is positive, right? And so that's why I made that assumption, just so that we can go ahead and do it. I'm going to follow the book and introduce a time when the population is m/2. So I'm thinking about actually even stronger than this. I'm thinking of a population that starts below m/2. So going back to our picture, I'm thinking about a population that starts down here somewhere, right? There's our starting value, and then it increases for a while, and increases for all time, but it's concave up for a while, and then it becomes concave down. And that moment when the population hits m/2, that moment I'm going to call t star. T sub star is the sign when the population is the time when the population has that value. And the nice thing about that is it lets us find this constant. That's essentially what we want to do. Find that constant c, and we're going to do it in terms of this kind of setup. So I'm going to take this on the next page. And you see the reason for doing that if I just plug in what we get when we make that substitution. So the population is m/2, so this becomes the natural log of m/2 minus the natural log of m minus m/2, which is in fact m/2. And then on the other side we get k t star, because that's the time now, plus c. All of this is 0, and so that tells us what c is. C is k t star in this setup. And that lets us take this expression and rewrite it with a c here. So we calculated that c, and we calculated what c was. C was k t star. All I'm doing is just plugging in to this expression up here for that value of c. Right? And so this kind of simplifies things. So we can write this as the natural log of, using the log laws, p over m minus p. I'm going to multiply this m on the other side, so this is k m t minus t star, and now it doesn't look quite so awful. I multiplied the m over, factored the k out, I used the log laws to simplify this. And so now we can solve for this thing. So this tells us that, in fact, P over M minus P is equal to e to the k m t minus t star. And t star is that moment when the population is exactly m over 2. And we can solve this. There's a bit of algebra here, but if I solve that for P, we end up with something that's kind of nice. We can write it as m divided by 1 plus that exponential e to the minus k. So this has ended up in the denominator. I've rearranged some things, but you can do the algebra. There is our population as a function of time, provided that you are happy to use this t star thing, which is the moment when the population is at half of the carrying capacity. So we can play with this. We can use this to look at the data that we had from the previous section, from the previous example where we had the exponential population growth. Now we've got some sort of population growth with carrying capacity. You can take this thing and plot it in Mathematica, and if I do that, I know it's going to have a general behavior that looks like this, right? So if I plot this curve, there's time, there's population, it's got to behave this way somewhere, and there's an inflection point at m over 2. We already kind of know what the graph looks like, but here's the formal function for it. Okay, so here's the Mathematica notebook, and the function I've just been deriving, that function we just found, here it is. I just defined it in Mathematica, and here's a plot of it with some particular choice for, well, I'm calling capital T, what's T star in the working, but this is, I should make this probably a function of T, but just plotting this thing as a function of T, where T star is this variable capital T, I set it to 50, and m is 100. I'm just picking random values here. I'm using r instead. I use k in the notes just to be really confusing here, but it doesn't matter. The idea here is that this function looks exactly like we expected it to, right? So let's have a look at fitting it to data. So remember on the way to that final formula on the previous page, we came up with this expression. It says the log of p over m minus p is equal to all of this stuff, right? So if I think about plotting that variable on the left, if I think about plotting on the y-axis that log combination, if I think about plotting it against time, what I'm going to see, if this is actually a variable, what I'm saying is I'm going to use this for my y and that for the x, and that means when I plot this, if it actually fits this model, the graph that I look at should have slope km, because there's the variable, and here's the multiple of the variable, which is the slope, and this is the y-intercept. So this thing is the y-intercept. So if I plot, and in this case by y I mean the log over p over that quantity, but this is a constant. K is a constant, m is a constant, t star is a constant. T star, remember, is the moment when the population is m over 2. M is the maximum carrying capacity of the population. I don't know that value, so I actually don't know m, so it's actually really, even if I have data on population against time, I don't know what m is. If I don't know what m is, then I can't actually build this quantity. But if I could build this quantity, then I could just plot it. If I saw a straight line, then I know the slope is k times m, and the y-intercept is this. So I know what m is, right? If I knew what m is, then I'd know the slope, so I'd know k. And if I know a k and an m, and I know the y-intercept, then I know t star. So I could find everything from that if I only knew what m is. So what do we do when nothing else works? We're going to guess what m is. We're going to look at the data. We're going to guess a value of m, and then we're going to see if we can get this curve to fit. So returning to the Mathematica notebook, here we see the population of the US plotted against time, again years. This is exactly the data we were looking at on the earlier video. And if this is leveling off, it's certainly not leveling off yet, right? Imagine this is an increasing function, and think about the shape of the graph we're looking at. Here's the logistic model plotted next to, this is actually the US population data that we were just looking at, right? Is there an inflection point here? Can we see an inflection point? If there's an inflection point, maybe it's around there somewhere, right? So maybe there's an inflection point here-ish at around 200, maybe around 250. It's really hard to tell, but maybe there's an inflection point going on there. And if there's an inflection point, then our model says the inflection point happens at m over 2. So if there's an inflection point here, it's around, well, it looks like 200, 250, something like that. let's make it 225. Right? That seems like a reasonable point to do it. In other words, maybe the data supports the idea that m is 450. Because maybe the data says we've got an increasing concave up function until about there, right? Increasing concave up, and then it starts being concave down. There's an inflection point. It's about 225. And so that's what I'm seeing here. This is 225, right? On this picture, I'm only seeing that much time. This is 2016, the last year we have data. Maybe things are going down. Maybe that's what we're seeing, right? The picture I have over here is this piece of the graph. So maybe I can support the fact that m is around 250. I'm just looking at the data and making a wild guess, because what else are we going to do? We're isolated and isolating anyway. So let's go back and look at the data. I'm guessing that m over 2 is 225. That's our inflection point. And so m is 450. Here's the data. I'm going to put m equals 450, and I'm going to plot a graph of the year against the log of p over m minus p. That's exactly what I said, a plot of p over m minus p, except I'm coming in and I'm writing 450 there. 450 million is our population, and now I need to find these other variables. So I'm just going to plot that graph. Oops. If I plot that graph, well, that's the actual population, and here's what we get, right? It looks roughly like a straight line. I mean, it's not exactly a straight line, but this is a better straight line than we were seeing before, maybe. The slope of the line changes a little bit after like 1930, but there's a pretty straight line going on there. So if I do a best, least squares fit, and I'm just going to use Mathematica's function to it, but I'm just doing the least squares fit to this line. What this model is showing is that the y-intercept's about minus 48 something, maybe 49, and the slope is 0.25. So taking those rough numbers, the slope, remember, is just k times m. And I know what m is. M is 450. So this lets me find k. K is whatever that number is divided by 450. So there's our value of k. And then the y-intercept, well, the y-intercept is minus k m t star. And I just told you what k is. There's k. So we can find t star. T star is going to be, what? It's going to be 48 over k, which we just calculated, times m, which is 450. So we can find k, and we can find t star, and we guessed m. So we have all the quantities in the model. And if you actually use the data in Mathematica, have a look at the notebook. I'll put it on Blackboard. This comes out to be essentially 1974. And so what that means that the population of the United States reaches half of its carrying capacity in about 1974, because remember, T star is when we're at m over 2. So if we say the carrying capacity, and this was kind of a guess based on the data, but the carrying capacity was about a 450, well, the US reached half its carrying capacity in 1974. That's what that number's telling us. If I go back to the equation, I know what m is, I know what k is, I know what T star is. We can plot this graph. And that's what I'm doing here in Mathematica with the actual data that we've got for the US population. And you can see that that's not an unreasonable fit, right? It does suggest that the US population is leveling off. Maybe there's if it follows this logistic curve, it's going to asymptote to a maximum population of about 450 million. That's what we came up with. That gives you an idea of how you can take a basic model, improve it, improve the assumptions, and then go about fitting it to data a little bit. So I'm going to give you an opportunity to do some of this in the coming homework. But in the meantime, I'll put a problem up for you to look at from the textbook to have some initial practice with these ideas. And some of those initial practice problems are going to turn up in the homework. But in the meantime, I hope you're doing well, and I'll see you on Friday.